surges becoming blocked, flow velocity dropping. Airflow stops because air strikes the compressor blades at too great an angle, causing turbulence and reducing lift. Stall is prevented by the variable guide vane system, reducing volume flow rate at low engine speeds. As you have seen, compressor stall can be destructive to the engine. Though automatic systems are designed to assist the engine in preventing stall, it is important you understand the concept of stall and the way the engine compensates for this condition. Stall and related surge will... This is Lesson 5, the combustor and turbine. Now we explore the basics of how the combustor and turbine sections operate. This lesson will take you into the engine's interior for a close look at the events of energy conversion. During these processes, you will observe the force of air converted to rotary power. You will also see how the engine handles unstable air conditions. At the end of this lesson, you may demonstrate your understanding by taking the progress check on the following performance objectives. 1. Describe the functions of primary and secondary air. 2. Explain the nozzle effect on the turbine function. 3. Explain impulse and reaction. 4. Describe the term surge. 5. Explain the function of bleed air valve. Here with this lesson is your instructor, Don Lovejoy.
It is in the combustor and the turbine section of the engine where energy conversion occurs and power is produced. Let's take a look at how this is accomplished.
The combustor has one primary function: to produce heat for the expansion of air. It does this by releasing chemical energy which is stored in the fuel. Ignition occurs when a spark is applied to this air-fuel mixture and burning begins. This is often called light-off. The total combustion process is divided into two steps. First, the burning of part of the air with fuel, and second, diluting the combustion products with the remaining air. It is in this second step that all the air becomes heated, causing rapid expansion, which is used to drive the turbine.
To see how these steps occur, let's look at the combustor. It's constructed like two concentric pipes. Combustion occurs between these inner and outer liners. One end of the combustor, the forward end, is covered, forming the dome, while the other end, the aft end, has shrouds which direct hot gases toward the turbine. Combustion takes place near the forward end. Combustion uses only about 1/4 of the air available at full speed. This primary air enters the combustor through many holes in the inner and outer liners. But most of the combustion air enters through air blast tubes located adjacent to each fuel injector boss on the outer liner. Here you can see how the blast tubes are associated with a fuel injector boss. The extreme temperature of the fireball requires some protection for the liners. Metal guides deflect some of the air to flow along the liner surface and to form a cooling blanket, so flames can't touch the liner. As combustion nears completion, toward the aft end of the combustor, the remaining air enters. This is the secondary air. Two important events occur here. The air cools the hot combustion gases before entering the turbine section, and the air is heated and rapidly expands. Without this cooling air, the combustor would be one big fireball at about 3,500 degrees Fahrenheit, and metals in the turbine section cannot tolerate such temperatures for long. Also, by using heat of combustion to rapidly expand the secondary air, a great increase in airflow occurs. Airflow that will directly turn the turbine to produce power. It is in the turbine section where power is finally produced. The expanded gases from the combustor turn the fan-like blades of the turbine, producing rotary power. The turbine has some features like the compressor. Rows of rotating blades, or rotors, are attached to a central shaft, while stationary blades are attached to the outer housing. The Centaur engine has 3 stages in the turbine, each consisting of a row of rotating blades and a row of stationary blades. Taking a close look at the stationary blades, we see they are not like stators in the compressor. The space between blades forms a nozzle. In the compressor, the space was more like a diffuser. The nozzle design is important to gain a high-velocity discharge from the combustor. The nozzle causes a significant increase in velocity and drop in pressure by converting heat and pressure energy into velocity. This high-velocity air is used in 2 ways in turning the rotor blades. The first is by impulse. Air is directed towards the blades, forcing them to turn away from the nozzle, turning the turbine shaft. The second is by reaction. High-velocity air expands as it passes through the rotor blades, pushing the blades in an opposite direction, again turning the turbine shaft. The Centaur turbine uses air in both ways, impulse and reaction. An impulse of air striking the leading edge of the rotor blade, and expanding air reacting against the blade's trailing edge. Both ways together maintain the evenness of the turbine's rotation at operating speeds. The expanding gases drop in temperature and pressure as they drive the turbine. The gases then exit through the turbine exhaust diffuser to atmosphere. Before leaving the turbine section, remember the turbine is designed to handle the large volume of air produced by the compressor and combustion, but only at high speed, what we call normal operating speed. During the start cycle, as the engine accelerates, the air produced by the compressor and heated in the combustor must all pass through a rather small passage, the first stage turbine nozzle. At lower speeds, the compressor is unable to build enough pressure to force all the discharge air through the turbine nozzle. At low speeds, the turbine is just able to power the compressor with the aid of the start system, and there is little power to remove excess air. If this is permitted to happen, a stall or surge condition will occur. Remember, in the compressor, stall was prevented by matching the forward and aft stages during acceleration. The variable guide vane system automatically adjusts for stall. But between the compressor and turbine, another solution must be used. Until the turbine has reached nearly rated speed, the excess air must be removed. This can be done by bypassing the turbine section. In doing this, we reduce the back pressure on the compressor and reduce the load on the turbine. The bleed air valve is used to direct about 10% of the air around the turbine section. Like the variable guide vanes, the bleed air valve is automatically controlled to open during the engine start cycle and close as normal operating speed is approached. Unstable air conditions occurring in the engine are generally called surge. So the anti-surge control during engine start rests with the variable guide vane system and the bleed air valve.
Let's review what you've seen. Primary air enters the forward combustor section, flows through air blast tubes, mixes with fuel and ignites. Secondary air enters the aft combustor section, cools the combustor gases, expands rapidly prior to entering the turbine. The turbine nozzles formed by the stationary blades increase air velocity and decrease air pressure. Impulse is the force of air striking the rotor blade. Reaction is the force of air escaping between the rotor blades, pushing the blades in an opposite direction. Surge is any unstable air condition in the engine. The bleed air valve removes back pressure on the compressor and removes load on the turbine during startup. The processes occurring in the combustor and turbine release a large amount of energy which is converted to rotary power. Impulse and reaction forces are used in this conversion of hot expanding gases into rotation. With this lesson, you have gained a thorough understanding of the